Okay, so hey everybody, thanks for being here today. Just going to say some things for people who are joining us in the future. For today's seminar, I got together a worksheet and we've spent the last 30, 40 minutes or so thinking about the worksheet individually. A couple of things that I would like to say beforehand we dive into the worksheet. Someone last week asked about this question 9. We talked about this question 9, which was talking about the product topology being the coarsest topology that makes the projections continuous. One thing that I forgot to say on Tuesday that I'd like to say today is that this problem was actually an old Qual problem. And I was going through old Quals looking for covering space questions to put on the worksheet today, and I found this question on an old Qual. So whoever asked this question has a good eye for asking me to review some questions, because this question was a Qual question, right? So I feel like that just deserved to be stated before we talked about stuff today. Okay, so today I suppose that I made a worksheet and I should show that I'm able to do the worksheet. Otherwise, I don't know, I deserve some sort of comeuppance or something. Okay, so you all who are here have been spending a little bit of time working on this worksheet. Where should we start?
Could we look at the second part of question 2?
Okay,
unless
the second
anybody
part
wants to see something before that.
So, yeah, so I uploaded this worksheet to the website. Okay, yeah, so the second part of question 2. So in question 2, we have P from E to B is a cover. E is connected. And what I want to do is I want to show if I have a finite K-sheeted cover over a particular point B, then the entire cover is actually that finite sheeted, right? Then this is equal to K for all. Right? That's what we're doing, right? We're saying that if I know the degree of the cover at one point, then I know the degree of the cover at all other points. Right? And note that once we prove this, this also shows that if a cover has infinite degree at a single point, then it's also infinite degree at another point. Right? Although the argument that I'm going to be giving today does not show that those infinities have to be the same cardinality, right? The argument that I'm showing today just shows that, like, hey, if you're finite in one place, then you have to be finite in all other places. So if you're infinite in one place, you have to be infinite in other places, but I'm not going to show that it has to be. It's true that if you're countably sheeted at a point, then you're countably sheeted everywhere, but that requires a slightly different structure. Okay. So the key step is to actually look at, so proof, or maybe this isn't the key step, but it's certainly a very important step. So by the exercises to know number 4, B is also a connected set. Okay. And we're going to now do a contradiction argument where we're going to assume that there are 2 different points where you're differently sheeted, right? And we're going to use those 2 points to form a separation of the space B, right? We're going to prove that B is not a connected space. So we're going to let U be equal to the set of all points B and B such that the preimage of B has k elements, and we're going to let, I should say assume for contradiction that there exists B1 such that the preimage of B1 is not equal to k, right? And then I need to define U and V in this way. So I'm going to let V be equal to B set minus. So then by construction, B naught is in U, B1 is in V, U union V is all of capital B, and U intersect V is equal to the empty set by definition. Okay? So I have almost everything that I want in order to form a separation of B. The only thing that remains to show is that these are both open sets. And the way that we're going to do this is almost the same as the argument that involved connectedness on Tuesday, right? Is that I'm just going to take an arbitrarily evenly connected neighborhood of a point in U, and I'm going to show that, hey, that's the entire evenly covered neighborhood is k-sheeted because a single point is k-sheeted, and it's a local homeomorphism on each of the slices, right? So there's one slice for every point in the preimage. So that means that the entire open set is k-sheeted. So the entire open set's contained in U, and that shows that U is going to be an open set. Right? Same story happens for V. So these are both going to be open. Is it worth writing out the details for you all? Should we move on to the next one? Or should I just write a summary of what I just said out loud?
I'm okay if you didn't do that, but
so the summary, then I'll just write the summary unless there are objections. Every point
Incidentally, I'm pretty sure this, I had a TA that said, you know, anytime you can do a proof directly rather than by contradiction, you ought to. But like, I'm pretty sure you can do this directly using essentially the same like sort of interaction between with Anthony, what happened in the case of showing that in Wilhelm's class, showing that yeah, something about basically a similar thing where you end up expanding an open region. You just say that you just take the collection of points like you have there where it's k-sheeted, then around every one of them you take such a neighborhood that the open cover guarantees you. Take the preimage of these, each one of those is open, and take the union of all of those. This is an open set, call it UK. This is a set of k-sheeted regions. Any other set must constructed in the same way must be open, and if you do that, you end up covering the set, covering the base, covering the domain. So in fact, since it's connected, you actually the header it expands to the whole region.
Yeah, now that you say that, I wonder if there's a way to not do the contradiction and just show that U is both open and closed. Right, because that would also prove this. So how would a closure argument work?
Basically, I'm saying like you don't want to do the argument inside B. You want to do the argument inside E. Because like, yeah, they're equivalent because, you know, images of connected spaces are connected, but it's easier to do it upstairs in E. Because you get openness and like the fact that it covers everything for free.
Yeah, so the statement that I was going to make at the end of this was that this statement is actually true if I only assumed that B was connected instead of E was connected. Right, so what I could do is I could take like a 2-sheeted cover of the circle with a disjoint union of the 3-sheeted cover of the circle onto the circle. Right, and then every point in here is all has the same pre-image cardinality of 5, right? But what you're saying is that, like, hey, then this forms a cover of my domain, and since my domain is connected, I get my result. But the proof that I want to write secretly is a proof that works even if I only knew that the codomain was connected, even if I had a disconnected domain, right? So yeah, so you are correct that I could push everything up into E and just extend the pre-image sets and be like, hey, these sets can't be separated, right? They have to overlap, and so therefore their cardinalities have to match. Yeah, so I suppose that I could, in fact, not use a contradiction argument if you didn't want. I could erase this sentence, right? And erase all of this bit and just show that U is both open and closed, right? Using the rest of the argument. And then say, since B is connected, right, U has to be all of B because it's not empty, right? So I actually do like this better than just constructing the separation explicitly, because all of this stuff takes space to write, but it's super easy. So why not just skip it? Yeah, so let's do that instead. I'm going to show that U is both open and closed by showing that U is open and V is open. Right? And it turns out that showing that V is open is the exact same argument that U is open. So let's just show that U is open. Right? So every point in U is contained in an evenly covered neighborhood with K slices. So the evenly covered neighborhood is contained in U. Right. Similarly, et cetera, with V ... not K slices. ... Right. So both U and V are open, which means that U is open and closed, i.e. U equals capital E. Yeah, so this is perhaps a nicer argument than my original argument, because as you mentioned, this does not use a contradiction argument. But for me, every time I see a statement that involves being connected or not, I always go, well, the way that we define something being connected is we say that it's not disconnected, right? So what I want to do is I just want to, like,
I don't
construct a
personally have much of an issue with using contradiction, but he ended up like mentioning it so many times that now I look for things. If I do it with contradiction, can I do it without?
Yeah. While I agree with that in practice, for the qualifying exam, you should just prove it whichever way you can think of to prove it. Right. Yeah, don't sit there in your qual and spend time being like, okay, I think I can do this with contradiction, but can I do it without? Just be like, no, just prove the question for your qual. But yeah, we can endeavor to be better. And this way I don't have to state all of these things that I crossed out in red, which is also nice. All right. All right, any other questions, comments, or concerns, or complaints? I don't know if you can hear my cat, but she really wants attention. I'm sorry, I'm teaching. All right, so third bullet point of question 2. So this was number two, I suppose. Okay, so for number 2, part 3, like I said, the first time, or when I was doing this last night, the first thing that I tried was wrong. Like I got there, like I did the thing, and I was like, this has to be the thing that works. And like do a restriction, yeah, to equally cover neighborhoods, take the preimage of those things. And then I was like, but how do I choose a point? Like I know that this open collection covers my preimage, but how do I know that I get something from my original cover that covers my thing? That was the thing that I got stuck on at first. I was like, how do I fix this? And I realized that it's because I did steps in the wrong order. So I'm going to spend a little bit of time talking about what didn't work, and then I'll give you proof of what did work. So if you're like copying down things that I'm writing, feel free to not copy down the next bit because it's the wrong bit. And then I'll tell you when I start writing down the right bit. Okay, so the first thing that I said is by above. The preimage of every point is equal to k for all A and B, and that's nice, right? And then I started off all these compact set proofs as one always does by letting script U be an open cover of the thing that I want to show as compact, right? Okay. So the next thing that I did was I said, okay, for every capital U and script U, P of U is open, right? Because every covering map is a local homeomorphism, and every local homeomorphism is an open quotient map, right? But not every open quotient map is a covering map. I mean, like these are, and in fact, not every local homeomorphism is a covering map. Although it's very hard to come up with examples where this is like you have to get to like really weird non-Hausdorff examples to get like the counter examples. So, like I'm not going to give you a counter example of this thing. Okay, so then what I did was I said, okay, for every B in P of U, let V be evenly covered. With B in V contained in U. Okay, and then I was like, okay, and then let script V, that doesn't look, be the collection of all such V. Then consider the all slices of all P inverse. So I'm not writing as much detail as I normally would, but that's because this is the wrong version, right? And I was like, this has to be the thing, right? I took an open cover, I pushed it down to the thing that I know is compact. I took a refinement to evenly covered neighborhoods, and then I took the preimage of those evenly covered neighborhoods, right? So, sorry, I almost did what I just said out loud, right? Take a finite subcover of script V and call it, because I'm lazy, script V. Okay, right? And I was just like, okay, cool. This is just whatever the cardinality of script V is times K open covers. And then what I want to do, right, is to, for every slice of P inverse V is I want to find U in script U containing that slice. But as I was trying to prove that this was true, I was like, this is not true, right? And so here's my silly example Y, right? So I'm just going to take like the 3-sheeted cover of a circle, right? And I'm just going to take the normal point here. So it has a preimage of these 3 points. And these 3 points might have, right, the following U's containing these 3 points, right? So I'm going to take like this set and this set, and maybe something like this set, right? And when I take the image of these 3 sets under this map, I get something like the image of the blue set is here, and the image of the red set is something like this, and the image of the purple set is like something like this, right? And so all that I'm doing, right, is for my finite cover, I'm choosing one of these sets, right? So let's say that I choose the red set as my element of V. Well, if I take the preimage of this element of V, then the preimage over this point is totally fine. But the preimage over this point is not contained in the blue set, and the preimage here is not contained in the purple set. And if I choose an open cover where these 3 open sets are the only points which cover these 3 points, then I can't choose a script U element correctly, right? And if I try to choose something that like intersects this thing or something like that, then how do I know that I didn't miss out on something somewhere else, right? That's kind of the problem. So the way to fix this is to take an intersection of all of the things that you need. Right? And you might be like, wait, how does taking an intersection of all the things that you need fix that? Well, hopefully it will be clear when I write this proof. So now I'm going to write the thing that works, or at least the thing that I think works. Maybe one of you will be like, Jacob, that's still wrong, which is fair. It's been a while since I've done these. Okay, so we're going to do the same thing. We're going to let script U be an open cover of E. I'm going to let P and B be arbitrary because it just makes the notation for the next couple of sentences a little easier. And here's what I'm going to do. For each E in the preimage of this point, right, there are K of them. Choose UE in script U such that E is in UE. And then what I'm going to do is I'm going to let V be an evenly covered neighborhood such, V sub B, I mean evenly covered neighborhood such that B is contained in V sub B, which is a subset of the intersection over all E in the preimage of this point across all of the images of the U's. Okay. And then you should say this on the qual because you want to dot all of your i's across all of your t's. So note, this is a finite intersection of open sets because P is an open map. Okay, and this essentially has fixed our problem, right? So if I draw the picture again, or actually, if I cheat, no, I'll just draw the picture again. I was thinking of copying and pasting, but if I draw the picture again, right? So I'm going to take the same 3-sheeted cover here. And if I try to draw some sort of approximation, maybe the colors are different or something. Right, so now what I'm doing for my evenly covered neighborhood, which I'll make a different color because it's different, is I'm just taking the intersection of these neighborhoods down here, and that's going to go to something which is contained in all of these 3 open sets. So then I can just choose the bigger sets which contain these, and then that will make sure that I cover the original points that I care about. Right, so that's kind of the fix here. Okay, so then, oh boy, I need more open set names. Okay, so then doing this for all B in B creates an open cover script V equal to all of these V sub B's. Let I equal 1 to N be a finite subcover. And let the set of U, I, J, where I ranges from 1 to N, and J ranges from 1 to K, be such that the preimage of each VI is the disjoint union from J equals 1 to K of the U sub I J's. Be the disjoint slices. And maybe you want to write this so that way you keep track of, like, maybe this is like B sub I and this is B sub I, so that you're still indexed by these B sub I's or something. But yeah, the notation here gets a little hairy. But now the idea is that every point up in your cover, right, is contained in one of these U sub B I's raised to the J's. And every one of these U sub B sub I's raised to the J's is contained in the original U sub E, right? And each U sub E was chosen as an element of the original open cover, so you just get an element of the original open cover, right? So construction. If E an element of P inverse of B, then U E an element of U sub B IJ. Yeah, so I'm just writing down the thing that I just said. Implies that U sub B sub IJ is contained in UE. Right, so so this creates a finite subcover of the script use. And last night I was running out of steam, and it was just like, that just sounds like a lot of really technical writing down, like lots of subscripts. So this is where I kind of stopped, but I can try to write out the really technical subscripts if you would like to see me suffer. Otherwise, we can talk about a different one of these problems. But hopefully at least the picture and this key step shows you like what the key step is, and the rest of this is something that you should be able to think through for the rest of this. And at some point you do need to take an intersection across the available candidates, right? Otherwise you run into the problem, like I said up here, where you can't choose a right open set, right? You know that there's a cover for all of these points in this open set, but you don't know how many you need for this particular open set, right? Because the open set's not compact. So that's details. All right, questions, comments, concerns? Okay, so we have 10 more minutes. Should I just do the last part of question 2? Should I do question 4? Should I talk about question 5? Rahul, is that a question or is that a vote for question 5? Vote for question 5. Okay. Or should I just give a blitz overview of how you do all of these? Like 3 sentences each.
I think looking at question 5 could be fun.
Okay. 5. Okay, so I mentioned this while the recording was off, so I will mention this again. Question 5 is easy if you have access to a collection of facts. Some of these are facts from part B, so I kind of added it at the end as like a segue to what we should talk about next week. But some of these are stuff that you can figure out just using stuff from part A. So here's a collection of some of the facts. And then Hassan said that I could use a good blitz. Okay, I will try to blitz through everything else at the end if I can. At least say like, here's the important step, or at least in my opinion, the important step for the last exercise of part 2. Yeah, and then part 3, I think is straightforward. And part 4 actually is more straightforward than the exercises in part 2. In my, and it's the actual Qual question, but I think that it's easier than slogging through question 1. Okay. Okay, so we need some facts. Okay, so the first fact 1 is that the figure 8 has a universal cover. Number 2, given if there exists a universal cover over X, then for all subgroups of the fundamental group, there exists a cover E over X such that the image, the induced map image, is equal to H, or at least is isomorphic to H. Number 3, every cover of a graph is a graph. And the last fact that you need is that the fundamental group of a graph is always free. Okay. So the proof is listing these facts in this order. Right. Okay, so there's slightly more details than this, but like it is essentially listing, right, these facts in this order, right? The fundamental group of the figure 8 is the free group on 2 variables, right? So you want to prove that every subgroup of this free group is free. So you take an arbitrary subgroup, right? You construct a cover, which realizes this subgroup, right? Then you say, hey, that cover, right, the induced cover, is also a graph, and therefore the fundamental group of that graph is also a free group. So I have a free group, right? That's essentially how this works. Okay, and then we maybe blitzing through the rest of these with our last 5 minutes. Number 2, part 4. Here's the outline. So the first thing that you need is that B is also compact. So I said while the video was off, I gave a hint for this last part that you need to restrict to a finite cover twice. Okay, so first you restrict to a finite cover in B, right? And then you restrict to a finite subset when you take the pre-image of your stuff in B. So you take the collection of all evenly covered neighborhoods has a minimal finite subcover. And minimal means that I can't remove an element of the subcover. And so that means that there exists a B in your base, and there exists a unique V in your finite sub collection, such that B is in B. Right? And this is what I think is the key step, because then for number 3, you take the pre-image slices as a cover of E, and you reduce to a finite subcover. And then the last thing to note is that by construction, only slices of the preimage of V can cover the preimage of your special point. Right? That's why I needed this to be minimal, right? The preimage of this point, right? The only thing that covers it is the preimage of capital V, right? Because no other element of my subcover contains little b, right? So since I have a finite number of these slices in my cover, that means that I must have had a finite number of slices of this set, right? So we conclude that the number of slices of P inverse V is finite. Right? And then that's how I get that the preimage of this specific point is finite. And then by the second bullet point of this question, the preimage of all of the points have to be finite because they all have to be the same. Okay. And then for question 4, although I'm very much running out of time, the idea is that you want to just construct disjoint. You want to construct evenly covered sets around each point in your base, right? So you choose y in y, and you consider the preimage of y, and you note that the singleton y is closed because y is Hausdorff, and so therefore this is closed and thus compact, right? Because every closed subset of a compact set is again compact, right? That's how we do this thing. So then number 2, what you do is so for every x in the preimage of y, you choose an open set such that, we'll call it u sub x, such that p restricted to u sub x is a homeo. And then you note that there's a finite number of such sets, or at least you can restrict to a finite number of such sets because it covers this compact thing, right? And then the last, no, it's not letting me choose the eraser, which is bunches of fun. Okay. Then the last thing that you note is that, let's see, what is last? Right. The last thing that you note is you define V to be equal to the intersection of all of the images of these UXs. Okay. These are all open because P is a local homeomorphism on these UXs. And so all these sets are open, so their images are open. Right? There's a finite number of these, so it's the intersection of a finite number of open sets, right? And the construction that you just did guarantees that the preimage contains the entire fiber. Right? So then you check that V is an evenly covered neighborhood of Y. And then that's how question 2 is. Okay, so I ran 2 minutes over. I'm sorry about that. Although the thing that I was going to announce is that everybody on the win to meet said that they were available to like noon on Thursdays. So if we run a little late, I'm totally fine doing that on Thursdays. And later in the summer, I will ask if you all want me to proctor future mock exams, or if you all just want to like take them as like practice problems. But if we do want to do a proctored practice mock exams, we'll probably do them on Thursday because we have a 3-hour block actually on Thursday that everybody said that they were available. So we can keep talking about math, but I did want to at least finish the majority of this worksheet before the end of the official time in case that changed and people want to leave, or if they're like, Jacob, we're not listening to you talk, which is totally fine. I don't pretend to be an expert on these, just someone who's thought about these problems. Questions, comments, concerns, or even just suggestions for what y'all want to talk about for part B next week. We can talk about that.
I had a slight question on one of the facts in, I think it was question 5.
Oh, okay, yeah, sure.
So I say every cover of a graph is a graph. Is that every connected cover of a graph is a graph? Because you could just have like a trivial like end sheeted cover, right?
Yeah, but that's still a graph.
Okay, so we don't require graphs to be connected.
No, a connected graph is a nice graph, but yeah, you can have a forced where you just have like
Okay.
a bunch of disjoint
Okay.
components. Yeah. So,
You mentioned that like Schultz usually draws from the same bank of problems.
Yeah.
Do we like, does anyone compiled that bank, or do we just have to figure out which years he's taught part B and go through and figure those out?
good question. So I removed this link from my, okay, so funny story, actually, I'm gonna stop recording. So goodbye if you're watching this in the future. You can ask me questions later.